Hello, and welcome to the video lecture for topic 18, E2, the one-step elimination. Now, unlike in the E1 reaction, the E2 reaction is a single-step process where removal of a proton by a strong base initiates loss of the leaving group and concurrently forms the new pi bond. Right? So this is one reason, the fact that we have to have the proton removed and the leaving group expelled simultaneously is one of the reasons that you have to use a very strong base for an E2 reaction. And we're going to get into that in a little bit more detail down the road, but I just wanted to point that out so that you know when you're looking at a reaction and you see a strong base being used for an elimination, that has to go by an E2 process, right? Because E1 allows weak bases or strong bases, E2 must have a strong base, and only a strong base will work. So let's take a look at what the overall mechanism is for this reaction. So we have some sort of molecule. We have a leaving group, which I'm just going to denote with an X. We have a beta hydrogen on this molecule, and we take our strong base, which I'm going to denote SB. Our strong base, we can recognize them because they have a localized negative charge on a single atom. That strong base is going to remove the proton. We're going to have the electrons in the carbon-hydrogen bond are going to form our new alkene, and at the same time, that leaving group gets expelled. So that overall, we end up with an alkene we formed a new pi bond. We have our leaving group. And we have our base, our strong base that has now picked up a hydrogen atom. So here I've had this negative charge passing all through my reaction. What you need to keep in mind is these strong bases are not just anions floating by themselves. They have to have some sort of counter ion that's positively charged. That's usually going to be a metal. And so that metal now comes here with its positive charge. Now we have a nice balanced reaction. Zero total formal charge on one side, zero formal total charge on the other. So to really get a good understanding of the E2 elimination and everything that goes into it, we need to consider four factors, right? And so the first thing that we're going to look at is factor number one is going to be the nature of the electrophile. Right? That's our carbon-based molecule that's got some sort of leaving group on it. I'm going to just refer to this as our electrophile, right? We need to look at what type it is. So when I mean type, what type of leaving group it has. We need to see whether it's going to be primary, secondary, or tertiary, because that's going to make a difference in our reaction as well, at the rate of our reaction. We also need to look at what we're going to call its conformation. And we're going to see how there are only very specific conformations for our electrophile that are going to allow us to do an E2 elimination. The second thing we need to take into consideration is going to be the base that we use. And we're going to look at both the strength of the base and we're going to look at the size of the base and see how that impacts the outcome and what our alkene product will look like. And then finally, we're going to look at reaction temperature and see how that's going to affect an E2 elimination as well. At the very end of this video lecture, I'm going to go ahead and give a comparison of E1 and E2 reactions, and also give a comparison of SN1 and SN2 reactions as a review leading into the exam. So, I'm going to go ahead and clear off, and we're going to start out by looking at different properties for our electrophile and how that affects the E2 reaction. All right, so the first thing that we need to look at is the type of electrophile, or the type of leaving group are on our electrophile. So here's one. We're going to look at the electrophile. And we're going to look at the leaving group specifically. So what I mean here is we've seen, for most of the reactions we've seen so far, SN1 and SN2, that we can use a few different types of substrates, a few different types of electrophiles starting out. We've seen that we can have alcohols, we can use alkyl halides, and we can also use sulfonate esters. Now, I'm going to examine these one at a time, starting with alcohols. So, if we take an alcohol with a beta hydrogen, so now our leaving group here would be OH. The first thing that should come to mind is that OH minus is a strong base. When this falls off, it'll form OH minus. That's a strong base, and strong bases are bad leaving groups. So we can't use alcohols to do an E2 elimination, right? And so we've seen before how we can form an oxonium, which will convert that OH minus bad leaving group into H2O, a good leaving group. So let's go ahead and do that. So if I bring this here now, I've formed now an oxonium. I've made my OH into a good leaving group by converting it into H2O. If I have a strong base, I need to compare the pKa's of all the acidic protons. So our proton here on our oxonium has a pKa of -2. The beta hydrogen that we want to remove for our elimination has a pKa of approximately 40 to 50. So it's very weakly acidic, whereas the proton on our oxonium is strongly acidic. And so our strong base is preferentially going to remove the proton on the oxonium, right? And the acid-base chemistry will happen. That's going to convert our base to a conjugate acid, and we can no longer do an elimination. So alcohols in all forms are ruled out for an E2 elimination. So put over here, no ROH for E2. Now, that leaves us with two other potential electrophiles, or carbon-based molecules with a leaving group. That would be our alkyl halides, and our sulfonate esters. Right? And so what we see here now is that in our alkyl halide, we don't really have any proton that's acidic enough to compete for the base. Right? We don't have the situation that we had here. I've got a proton with a pKa of -2 versus a proton with a pKa of 40 to 50. In these two cases, both alkyl halide and sulfonate ester, I no longer have an acidic proton that's going to be competing for my strong base. And similarly, I now have leaving groups that when they fall off during the elimination form very weak bases, right? We know that X minus is a weak base. We know that sulfonate esters, or the conjugate base of a sulfonate ester, is also going to be a weak base. And so these work perfectly well for us to do E2 eliminations, right? So in terms of the leaving group, we can't have ROH for an E2, but RX and sulfonate esters, our alkyl halides and our sulfonate esters, are excellent starting materials. So no ROH, but these two work well. So that's really good for us. We now have a system with a leaving group where we can easily deprotonate that and get it to go through the E2 elimination. So the next thing we need to look at is what the degree of substitution at this alpha carbon is going to be, and how that affects the rate of an E2 elimination. Going to clear off, make a little space, and be right back to talk to you about that. So in terms of the degree of substitution at that alpha carbon, we can have three types of electrophiles. We can have a tertiary electrophile, So there's my beta hydrogen. Here's now my carbon with my leaving group. And I'm going to go ahead and make that tertiary. And we could also have a secondary. So here now, with my leaving group on my alpha carbon, one hydrogen, and another R group, that's going to give me a secondary. We can have a primary. So now I've got two hydrogens there. And finally, I could also just have a methyl. Now, I'm going to start with the methyl and then come back up to the tertiary. And the reason for that is we should notice right away for our methyl that there is no beta hydrogen. Remember, the carbon attached to the leaving group is known as the alpha carbon, and an elimination requires the presence of a beta hydrogen because that's the hydrogen that gets removed during the process. And so because we have no beta hydrogen on our methyl electrophiles, they cannot react by an E2 elimination. In fact, they cannot react by an E1 elimination either. So we can rule methyls out. Now what we want to do is compare our primary versus secondary versus tertiary to see which one of these is actually going to react the fastest. Now, after elimination for my tertiary example, what we see is that we are left with an alkene. And I'm now just going to be referring to the alpha carbon, right? So this was the alpha carbon from our starting material. And we see that there are now two substituents on that alpha carbon, two non-hydrogen substituents. So we can say that the alpha carbon is disubstituted. For our secondary example, and again now I'm just referring to the alpha carbon, we see that we're left with a hydrogen and one non-hydrogen substituent. And so we can say that the alpha carbon is monosubstituted. And then finally, for our primary, what we'll see is that our alpha carbon has two hydrogens on it, and so we can say that our alpha carbon is unsubstituted. Just like in an E1 reaction, the compound that will form the most substituted alkene is going to be the one that reacts the fastest. We can think about this also in terms of the transition state of what's occurring, right? While this process is happening, we're losing the hydrogen. The electrons from the carbon-hydrogen bond go to the carbon atom, while simultaneously the leaving group begins to depart and it takes its electrons with it. That means I'm starting to develop a partial positive charge on that alpha carbon during the transition state. And we know that a partial positive charge is going to be stabilized by R groups better than it's going to be stabilized by hydrogens, right? And so our tertiary not only provides us the most substituted alpha carbon, but it also gives us the most stabilized transition state. And so tertiary electrophiles are going to react the fastest. Primary electrophiles are going to react the slowest. And methyl electrophiles do not react in eliminations, E1 or E2. So now to keep going with what we're looking at our electrophile here, we have no ROH for an E2. We have to use alkyl halides. We have to use or sulfonate esters. We can add on to that for our degree of substitution, we'll call it. We can say that tertiaries are faster than secondaries, which are faster than primaries, and that methyl don't work. All right. So that's our second piece of information that we need to know about our electrophile. So now the final thing that we need to talk about is the conformation, the starting conformation of our electrophile in an E2 reaction. And that's going to predict for us what our stereochemistry for our major product is going to be. So again, I'm going to clear this off, and I'll come right back and we'll take a look at how conformation impacts the E2 reaction. All right, so the last thing we need to take a look at in terms of our electrophile is its conformation. All right, so this really has to do with what's happening in the transition state of an E2 reaction. And so that's what I'm going to go ahead and draw up. So here we have our base. Excuse me. We have our base. I'm going to bring those electrons in just a moment. We have our beta hydrogen. We have our beta carbon on our alkene. We have our alpha carbon on our alkene. Oops. We'll bring that bond in just a second. We have our leaving group, and we have our other substituents on our alpha carbon. Excuse me. Now, what's happening during this reaction? Well, the base is beginning to form a bond to our beta hydrogen. The bond between the beta hydrogen and the beta carbon is beginning to break. The pi bond is beginning to develop between our two carbons, between our alpha carbon and our beta carbon. And the bond between our alpha carbon and the leaving group is beginning to break. So let's go ahead and think about what sorts of partial charges are starting to develop in this system. Well, this hydrogen, we can think, is beginning to lose its electrons, so we'll go ahead and give it a delta plus. Those electrons are being left on our beta carbon. We'll go ahead and give it a delta minus. This bond here between our alpha carbon and leaving group is beginning to break, and the leaving group is taking the electrons. So we'll give it a developing negative charge, and our alpha carbon will get a developing partial positive charge. So in terms of electron flow and partial charges, we have now a sense of what's happening in this transition state. But we can also think of what's happening in terms of hybridization on both our beta and alpha carbons. And so both of these carbons are going from sp3 hybridization to sp2 hybridization in the final molecule. And remember that a pi bond can only be formed by the side-to-side overlap of two p orbitals. That's why we're going to end up in a sp2 hybridization. But now we can take a step and think, what does this transition state need to look like in terms of there was an sp3 orbital on this carbon and an sp3 orbital on this carbon. Theirs are going to need to end up being parallel p orbitals in our final product. And so if we didn't have this good orbital alignment, we would have one p orbital from our beta carbon with 2 electrons in it. But in our alpha carbon, out of plane, right, not parallel but perpendicular or some other orientation, would be our other p orbital on our alpha carbon. These orbitals are not situated such that they can overlap side to side to form a pi bond. And so what we need to have is not this, but we actually need to have our orbitals aligned parallel, and that's going to allow us to go ahead and form a pi bond. Now, how can we ensure that these two p orbitals end up parallel? Well, what we want, if we take a look at our molecule through a Newman projection, what we're going to want is we're going to want our beta hydrogen and our leaving group to be anti to one another in a Newman projection. So I'm going to draw a Newman projection for this molecule, and I'm going to cite in this direction down the carbon-carbon bond. So that's going to be my alpha carbon will be my front carbon, my beta carbon will be my back carbon in the Newman projection. So let's go ahead and get our Newman projection started. Excuse me, let's clean that up. So in our Newman projection, ideally what we want to have, here's our front carbon with our leaving group. We want our beta hydrogen to be anti to that leaving group. This way, these orbitals, right, the sp3 orbital from my front carbon and the sp3 orbital from my back carbon, those are going to be already aligned in space, and once they undergo rehybridization to make p orbitals, they're going to be parallel, and they're going to allow me to have good orbital overlap to make that new pi bond, the orbital overlap that we're looking for displayed here. Recall that this conformation is called anti-periplanar. Now, there is one other conformation that has the leaving group to alpha carbon sigma bond and beta hydrogen to beta carbon sigma bond, both also aligned parallel. And that's going to be our syn-periplanar conformation. So if I rotate that back carbon 180 degrees, so here my front carbon, I still have my leaving group down, and here are my other substituents on my alpha carbon. But now, if I rotate this back carbon 180 degrees, I can put my beta hydrogen parallel to my leaving group. However, you see why this is an unpleasant conformation for the molecule to adopt. There's a lot of steric hindrance between all the other groups, right? Between these R groups and these R groups, we have torsional strain, we have steric strain. And so this is a very high energy conformation, not likely to be populated in the reaction, right? But a little teeny bit is going to be, the small population of our sample will be aligned this way and will be able to undergo elimination, right? Remember, this conformation is called syn-periplanar. And so our syn-periplanar conformation, because it has a very small population in our sample, this is going to be a very minor product. But our anti-periplanar, little to no steric hindrance, no torsional strain, right? This is always going to give us our major product from our eliminations. Being able to do this analysis from a perspective drawing to a Newman projection is going to go a long way to helping you predict what products are going to be the major and minor products from an E2 elimination. This is especially important when you come to look at cyclohexane systems, because doing a double Newman projection for a cyclohexane system will allow you to determine which of the two chair conformers has the leaving group anti to the beta hydrogen, right? And you can only achieve anti-periplanar in a cyclohexane, whereas in a non-cyclic system, you can achieve syn-periplanar occasionally. So what I'm going to do is I'm going to clean up the board just a little bit and walk through an example that shows us how this type of alignment can help us to predict what our major and minor products from an E2 elimination are. So I'm just going to show one example, but I highly recommend that you work through a lot of these on your own. It's really going to give you a sense of how to be able to predict. So let's just take a hypothetical alkyl halide. Here I'm going to put hydrogen in plane. I'll put a methyl group going behind the board, put a phenyl group coming out of the board. That'll be my beta carbon. Here now I'll put in my alpha carbon, and I'll put a bromine coming out of the board, a phenyl group going behind the board. Oh, excuse me. Make that a hydrogen going behind the board. We'll make this, pardon me, a hydrogen going behind the board. And finally, we'll have a phenyl ring in plane. Now, we can see that our leaving group, the bromine, is not aligned either syn or anti-periplanar with our hydrogen. And so if we want to translate this now into a Newman projection, and here now I'm going to sight down from the beta carbon to the alpha carbon. That's just because that's how I prepared my notes. Really doesn't make a difference. You can cite from the alpha to the beta or from the beta to the alpha. The end result will always be the same if you set up your Newman projection correctly. So now citing from my beta carbon to my alpha carbon, it's going to make my beta carbon my front carbon. See that I have a hydrogen up. I'll put my methyl group to this side, and I'm putting my phenyl group to that side. So again, I'm looking this way, right? And that's the orientation that I would end up with. Now, on my alpha carbon, which is going to be my back carbon, my phenyl group is eclipsed by that hydrogen. My leaving group, the bromine, is eclipsed by that phenyl ring. And then finally, my alpha hydrogen here is going to be eclipsed by that methyl group. And so now we can clearly see that the beta hydrogen and the leaving group are not either syn or anti-periplanar. So let's go ahead and rotate that beta carbon a bit to get it into an anti-periplanar conformation. So here now, there's my beta hydrogen. I've kept my front carbon stationary while rotating my back carbon. That rotation of my back carbon puts my leaving group anti to the hydrogen, to the beta hydrogen, and moves my other two substituents to these positions. Now when I actually go ahead and do the elimination, right, so this is my anti-periplanar conformation. When I do this elimination, those two atoms are going to get removed, my beta hydrogen and my leaving group, and this tells me what the stereochemistry of my alkene will be. On one face of the alkene, I'll have my methyl and my hydrogen, and on the other face of my alkene will be my two phenyl rings. And so then this now is going to be my major product, which actually has a Z conformation. Recall from the E1 elimination, because we go through a carbocation intermediate, that molecule can adopt the lowest energy conformation that places the two largest groups on the alkene in a trans or E relationship to really reduce steric hindrance. But because my E2 elimination is all in a single step, right, the anti-conformation is what's going to be my major, which is what's going to lead to my major product, because the syn-periplanar has a lot of strain in it. And so so using an E2 elimination, I can actually make a Z alkene be my dominant product, depending on my starting stereochemistry of my electrophile. And so we can go through lots and lots of examples of this. This is the basic process. Just to quickly show you from the syn-periplanar conformation, here now in syn-periplanar, again I'm keeping my front carbon the same. This time now I've rotated my back carbon in this direction such that my bromine is eclipsed by that beta hydrogen. So there's my bromine eclipsed by the beta hydrogen. That's going to put now phenyl ring by the methyl and hydrogen by the phenyl ring. Again, I'm going to eliminate these two atoms, create my alkene, and what I see now is that I have on one face of my alkene my methyl group and phenyl ring. So here once again, I didn't move that front carbon, so my methyl group will end up in the same place. But now, on what was my alpha carbon, my phenyl ring is on the same side as the methyl. And if we look what's happening on this side, my phenyl ring is eclipsed by my hydrogen, so they are on the same face. This now gives me the E alkene, but this is going to be a minor product. So, adding to our list of rules and things we need to consider, we now know that anti-periplanar gives us our major product, and syn-periplanar gives us our minor product. So I recommend that you go through this exercise with a few different molecules, right, where you can see how if I just change the stereochemistry at one of these two carbon atoms, so that you know right now we have S and S. If I change one of those to R, we'll see that this ratio ends up flipping, where the E becomes the major and the Z becomes the minor. And I'd like to leave that exercise for you to do. Walk through this process using one of the opposite by only changing one stereo center on our starting material. Okay, so that covers what we need to think about in terms of the electrophile. I'm going to clear off and we're going to start taking a look at what we need to consider in terms of the base that we use. I mentioned at the beginning of the video lecture that the E2 reaction requires a strong base. And I'm not going to go much deeper into that other than to talk about very quickly what makes a base a strong base. Well, strong bases are going to have a localized negative charge on a single atom. And our choices that we're going to look at are going to be that negative charge on a hydrogen. This would be a hydride. That negative charge on an oxygen. So this could be hydroxide or the conjugate base of an alcohol. This could also be on a carbon atom itself. Or it could be on a nitrogen. So these are what we're going to see in terms of strong bases used in E2 eliminations. I'm going to focus on the two that we're going to look at most commonly, which are going to be our alcohol or hydroxide and alcohol bases and our amine bases. Now, when we take a look at these, right, we're going to consider now, we've determined the strength. All of these are very strong bases, have to have a strong base for E2. So let's just now look at the size of the base. Now, when thinking about the size of the base and how it impacts it, we should also take a look at the electrophile. So I'm going to draw here a potential electrophile, and I'm going to put only one beta hydrogen on this carbon. Here's now my leaving group. But I'm going to create a second beta carbon and a third. Now, when thinking about the size of the base, we have to consider what is the degree of steric hindrance around the beta hydrogens. So again, here we have two different types of beta hydrogens. We're going to ignore this one down here because this one and this one end up in the same result. So when we're thinking about this, we can compare two different sized bases. So let's just take a look at alcohol bases. So hydroxide relatively small versus tert-butoxide. Now, what you should notice right away is that tert-butoxide, these methyl groups are creating a great deal of steric hindrance around this oxygen. It's relatively bulky. The whole molecule, this whole base, is pretty big and bulky. And hydroxide, the oxygen only has a little tiny hydrogen atom attached to it, so it's very small. Now, when we look at our two beta hydrogens, this one here is very deep within the molecule, and it's got, lots of big groups around it, and so this is a sterically hindered beta hydrogen. Whereas this beta hydrogen out here is relatively exposed. It's on the outside, on the periphery of our electrophile. And so our small base, our hydroxide, is small enough that it can reach into that beta hydrogen, or it can reach into that beta hydrogen. Whereas our bulky base, tert-butoxide, can only reach this outside beta hydrogen. It's too big to get into this trapped, sterically hidden beta hydrogen. So if we look at what the products from these two would be, so here I'm just now going to draw an arrow. This is going to be my product from OH. we see that when I use OH minus, I can make this alkene and that's going to come from arrow number, whoops, let's actually put our alpha carbon in there just for clarity. Right, so this is going to be from arrow number 1. I have made here now a tetrasubstituted. From arrow number 2, I can also make this alkene. So here now, I actually deprotonated from this beta carbon. And what we see is here now, we have made a disubstituted alkene. So that's from arrow number 2, we get a disubstituted alkene. So using a small base, we can make a tetrasubstituted alkene. Recall that the higher degree of substitution, the lower potential energy of alkene. So our tetrasubstituted will be our major product, and our disubstituted would be our minor product. Now, looking at what the result would be using my bulky base, tert-butoxide, it can only really reach one of these protons. It's too sterically hindered to get after the internal beta hydrogen, right? And so using tert-butoxide, our disubstituted alkene has now become our major product. And even though it is big and bulky, it will be able to occasionally reach that proton. And so our minor product, we can say, is potentially the tetrasubstituted alkene. So this is our major product, and our tetrasubstituted is the minor product. And so this is with O minus TBU. So now we can see how using a different base, right, changing the size of the base can really affect what the outcome in terms of product distribution is. So one last thing here, when we use a small base, right, so this is now using a small base, we see that the tetrasubstituted alkene is going to be our major product. And remember, the most highly substituted product is known as the Zaitsev product. Right? So we'll put a little note over here. Small base, our Zaitsev is going to be the major product. And because we can create these less substituted ones, we actually have a name for this product when it's the major product. We call this the Hofmann product. And so we now know that using a bulky base makes the Hofmann product our major product. Okay, so we've seen examples of a small base and bulky base for our oxygen bases. How about a couple of examples for our small bases and bulky bases for our nitrogen examples? Alrighty. So for nitrogen, we can have a typical small nitrogen base would be deprotonated ammonia. So this is going to be NH2 with 2 lone pairs, and this usually comes along with a sodium cation. And for a bulky base, for our nitrogen bases, there's an important one that I really want you to know. It is a base that is very frequently used in organic chemistry. It is known as, so there's a positive on a lithium, negative on a nitrogen. This is known as lithium diisopropylamine. This is a bulky, sterically hindered, but yet extremely powerful base that is routinely used in organic synthesis. And we typically abbreviate this as LDA. This is a base that you're going to need to know for Chem 201. It's also going to come back around and show itself in Chem 202. So get familiar with it, learn it, love it, and you'll be using it all the time. All right, the last thing I'm going to say before I get into a comparison of E1, E2, SN1, and SN2 is that just like we saw for E1, heat favors elimination. So whenever you see a reaction arrow and you're trying to decide between E2 and SN2, you see heat as a symbol, E2 is the direction you're going to go. Elimination is always promoted by heat. Now, in terms of which product you're going to end up forming, that you're going to have to check your base for. All right, so all that's left for this video lecture is to do a quick comparison between E1, E2, SN1, SN2, and I'm going to clear off the board. We're going to go through all that here and wrap this video lecture up. All right, so let's compare our 4 reactions that we've seen so far. So we have seen E1, E2, SN1, and SN2. So some of these, I'm going to do these a little bit separately, so we're going to just kind of have ourselves a little dividing line here between the 2 sets of reactions. And let's go through E1 and E2 first. So for our elimination reactions, one of the biggest things we need to consider is going to be the base. And we've seen that E1 tolerates and is perfectly happy with a weak base, but for E2 it can only be a strong base. Now, in terms of solvent, E1 goes through a carbocation intermediate, and so that means we're going to need to have a protic solvent. Whereas E2 all happens in a single step, so solvent here is not important. All right. Now, in terms of our electrophile, I'm going to call this the R leaving group molecule. We've seen that for E1, tertiaries react faster than secondaries, but primaries don't go through an E1 process because, right, they can't form a carbocation. In E2, we saw that the degree of substitution on our R leaving group molecule led us to see that tertiaries react faster than secondaries, which react faster than primaries. In both cases, methyl R leaving group never works. All right, now in terms of the rate law, E1 is a unimolecular process, and so the rate is going to be equal to some constant times the concentration of our R leaving group, whereas for E2, because we have both the base and our R leaving group molecule involved in a single step, our rate law is R leaving group concentration times the concentration of base. Unimolecular reaction, bimolecular reaction. All right, now finally in terms of our product substitution, we see that in E1 we always get the Zaitsev product as the major product, whereas E2 we will get the Hoffman as the major product. So this is Zaitsev major always, whereas the Hoffman product is major product with a bulky base in the E2 reaction. In terms of conformation, so this is going to be our R leaving group conformation. In an E1, because we go through a carbocation, this here is not important. Whereas in an E2, the antiperiplanar leads to our major, excuse me, antiperiplanar will give us our major product. And again, it must be either antiperiplanar or synperiplanar to go through an E2. And then finally, rearrangements. Right? E1 goes through a carbocation, so rearrangements in an E1 are common. E2 does not go through a carbocation rearrangement, so this never happens. All right, so that takes care of comparing the major factors in E1, E2. I'm going to get some extra lines here on this table just so that if you decide to copy it down, it's a little bit more clear for you. All right, now let's take a look at SN1 versus SN2. And again, we're going to kind of do a similar table to this. So now for SN1 and SN2, first thing that we want to take a look at is going to be our nucleophile. And we saw that in SN1, we can have a weak nucleophile, is okay. Whereas in SN2, we must have a strong nucleophile. So this must be a strong nucleophile. The next thing we want to take a look at is going to be our electrophile. And we saw in SN1, our order of reactivity for our electrophile is going to be our benzylics are faster than allylic, which is faster than tertiary, which is faster than secondary. For SN2, we saw that methyl is faster than primary, which is faster than secondary. Let's just get a dividing line there so that we can keep them separate. Next, for SN1, SN2, we need to consider solvent. And we saw that in SN1, we need a protic solvent to stabilize that carbocation and sequester our leaving group. Whereas in SN2, we want to actually have an aprotic solvent. And I'm just going to put here polar underneath the solvent because SN1 polar protic, SN2 polar aprotic. Going on from there, our rate law for these reactions. For SN1, we have a unimolecular reaction, so that's going to be dependent only on our R leaving group. Whereas in SN2, because we have a bimolecular reaction, that's going to be dependent both on the R leaving group molecule and on the concentration of the nucleophile as well. So let's just remember that electrophile, this is our R leaving group molecule. And let's get some more lines in here. Keep this nice and hopefully divide it up so we can tell what's going on. So after the rate, the next thing we need to consider for SN1, SN2 is going to be product stereochemistry. We saw in SN1, right, because we go through that carbocation intermediate, which is planar, nucleophile can approach from either face, we end up with a racemic product. Whereas in SN2, because the nucleophile has to approach opposite to the leaving group, we always end up with inversion of stereochemistry. And then finally, last thing we want to take a look at is the possibility for rearrangements. And because SN1 goes through a carbocation, rearrangements are common. Whereas SN2 does not go through a carbocation, so here rearrangements never happen. All right, so hopefully that kind of collects, I'd say, 60% of the information you need to know. The rest of the information you can get from that decision tree that I distributed earlier in the semester on SN1, SN2, E1, E2 to kind of help you see what pathways different molecules can go through and how different reaction conditions can drive for one pathway versus the other. All right, So hopefully this has been a beneficial video lecture for you. As always, if you have any questions, please feel free to bring them up in lecture, conference, come by for office hours, or make an appointment to see me one-on-one. Thank you.